Right. Welcome to DSP. Today is the 18th of February. We are on week 6 now on Thursday. So basically, for today's lecture, what I'm going to do is I'm going to do the CE3007 exam paper, one of the question. So first I will share my screen. This is the exam paper that I'm going to do. Is May 2019. So this is the exam paper, and this is the question. Now, in the exam papers, as for this year, it will be the same. It will be a restricted open book. Basically means that you are allowed one two-sided A4 paper containing self-prepared notes. Okay, and we give you some formulas, but we expect that your self-prepared notes would help you. Right? You can put any tables or any equations that you want, and theory as well. Now, we'll do this question. Question 1 is 25 marks and question 2 is also 25 marks. You should be able to do it within half an hour. Okay, so this is what we are going to do. All right. So I hope that this is being recorded. Let me check. Yes, this is being recorded now. And is everyone looking at my screen, guys? I don't want to be like the US professor. Can somebody tell me, please? Chat. Sebastian, you can hear me, right? Okay, great. Okay, you can see my screen as well. Okay, good. So now I would pull out this question, and then I would also pull out my, what do you call it? My iPad. So now you'll see the question and the answer side by side first. I know it's very small, but let's bear with it first, and then I'll write the question down. Okay, let's begin. So this is CE 3007 2019 May exam. Question 1. And I will write down the question. The LTI system is given by yn equals to xn plus x of n minus 1 plus 1.6 y of n minus 1 minus 0.89 y of n minus 2. Now, when you see that I have given you an equation like this, and then the first one I'm going to ask you to draw is pole zero diagram. Now, if you have issues with this, you should go to the lecture notes. Now let's pull out the lecture notes of exactly which lecture notes will be able to help you. So go to the lecture notes in lecture slides, and it will be on O4A Z transform in this lecture note. In the second last page, you will realize that I have given a very, very similar question here. Okay, now this question is simpler than the exam. In this question, you have xn plus xn minus 1. You realize that xn plus xn minus 1. The only difference is that in this equation, we only have one feedback for yn, while in the exam, we have two feedback. Right, so it'll become a little bit more difficult technically, but everything else is the same. So now I'll take the chance to redo the whole question again, and you realize that the whole question can be completed in like 2 slides. Okay, so let's try. So the pole zero diagram he's asking you to do is you should be also looking at this picture. In this picture, it is the very big overview of our Z transform and the concepts attached to it. We begin with the difference equation here, and then we are asking you to draw, the first question is pole and zero diagram. To reach here, you must follow the arrows. You must convert the difference equation into the system transfer function, which is hz. And then from the system transfer function, you'll find the poles and the zeros of this system transfer function, and you can draw hz. Okay, let us now try to do this. So perform z transform. Yn become yz, xn become xz plus x of z, and n minus 1 becomes z minus 1 plus 1.6 y of z minus 1 minus 0.89 y of z minus 2. And then you collect all the yz's to one side. So this is 1. And then you have minus 1.6 z minus 1. And you have plus 0.89 z minus 2. And the other guy is 1 plus 1 z minus 1. Finish. And then to get the next equation, we want to get h of z, which is nothing but y of z over x of z. And then you can realize that this is what you're trying to do, which is that this is the numerator and the denominator is this. Now, many students become stuck here because they do not know how to proceed onwards to simplify this equation. And you realize that what we are trying to ask you to do is to do factorization. So to do factorization, we don't like to deal with negative power of z. So what do? We multiply top and bottom by z square. So this guy is of course 1. So nothing is changed. And you get z square plus z on the top. And the bottom is z square minus 1.6z plus 0.89. Okay, so I'll pause here now, and then any questions, guys? No? Okay. Are you still with me, guys? Yes? Maybe Sebastian, tell me. Great, thank you. All right, if you're still with me, then we're almost done, really. So to simplify, we have z times z plus 1. And then the bottom, you realize that, hey, if you forgot how to do factorization, then, well, you must learn, because if, then the answer is 0.8 plus 0.5j z minus 0.8 minus 0.5j. So this step to this step, yeah, is just factorization. Okay, so you must be able to do. And what it means is that, so let's write h of z here, and therefore the zeros of h of z, what does the zero mean? It means that the value of z such that h of z becomes 0. And then of course you realize that when z is equals to 0, the numerator becomes 0, so everything is 0. And when z is equals to minus 1, so I should change my pen. So when I put z equals to 0 here, everything becomes 0. When I put z equals to minus 1 here, everything becomes 0. So, okay, so this is my zeros. What about my pole? So the poles of hz means the values of z such that the denominator of h of z. What's the denominator? So the denominator of h of z is, where is this guy? So this guy is the denominator of h of z. So when z is equals to 0.8 minus j 0.5, then this guy becomes 0. So something over 0 is infinity. So implying these are the, so z equals to 0.8 minus j 0.5 is a pole. The word is a pole means that h means, what does means? Means that h of z becomes infinity, because something over 0 is infinity. Now you realize that once you have found one of them, The other guy is very easy to find because this is simply the conjugate, 0.8. So this is should be plus, right? Yep, J 0.5. And then we are done. Therefore, Z is equals to 0.8 plus J 0.5. So we have found the poles and the zero. So we have found this guy, which is the pole. We have to found the zero, and now we can draw the, what do you call that? The pole zero diagram of H of Z. So what is the pole zero diagram? Okay, you must understand the concept. The pole zero diagram of H of Z is drawn on the complex number Z. Z is a complex number. So this is the real part of the Z. This is the imaginary part of Z. So this whole surface is the complex plane. Yeah, that means I can now tell you any complex number on this plane. All right, so what about, where's the number zero? Number zero is here. Zero is here. What about this guy? This guy is number one. Or this guy number two. If this guy is number three, therefore you can guess what is this guy. Minus one, right? And minus two, and so on. Wait, let me see. There's somebody coming. Okay, nobody else is coming. And minus three. Now you have this guy is J, and this guy is 2J, and this guy is minus J, and this guy is minus 2J. Once you have that, then you can draw a circle. This is called the unit circle. This is, you must draw it nicely, and then this unit circle have radius 1. And now we are here to draw the pole and zero diagram. So let's remember what are our values. So this is the value we're interested in. Z equals to 0, Z equals to minus 1. Where Z equals to 0, let's choose a different color. Z equals to 0 is here. So and 0 equals to minus 1 is here. So these 2 points, so Z equals to 0 is Z equals to minus 1. What else do we have? What about the pole? The pole is sitting at 0.8. Oh, I made a mistake. 0.8 is here. 0.8. 0.8 plus minus 0.5. Okay, where's 0.8? 0.8 is about here. 0.8. 0.5 is here. So I draw one cross here and one cross here. So this guy is 0.8 plus J 0.5, one pole. This guy is 0.8 minus J 0.5. So this is the pole and zero diagram. Now let's look at the exam question again. The exam question says we have to sketch the appropriate ROC and state the stability. So you have to expand this. The ROC in our example is, first you draw a circle of the radius that touches these two poles. And because our, what do you call it? Because our system is a causal system, and the ROC is external to this circle. So this hairy thing is external to this circle. And then we say this is ROC. And then we say that the system is stable. Why? Because the ROC includes the unit circle. So if you want to be very pedantic, ROC is external to the furthest pole. Okay, because the system is causal. Okay, so here the word system is because the impulse response exists on right hand side. So you have to figure out all this in the lecture notes. of stability. So you see, that's it. Uh, Within, one small page, you can get the 6 marks done. Any questions, guys? All right. No, then we'll proceed to do the second part of the question. Now, the second part of the question says, by inspection, suggest the type of filter. This will make this to understand this concept. You have to understand uh, how to interpret this figure. Okay, what I'm going to show you is this. I'm going to trace along this line. So I'm going to trace. Can you see my orange here? And I'm going to trace along this line, which is on the unit circle. And you realize that I have started when I've started from omega equals to 0, and then I move along anti-clockwise. I reach omega equals to pi over 2, and finally I reach omega equals to pi. Okay, now as I move along this omega, along the unit circle, I am examining my pole and zero diagram at different frequency. Okay, so actually, uh, you can also understand it from this point of view. You go from 0, pi over 2 to pi for different omega. So as you are traveling along this line, you're traveling also along this line in this picture of the unit circle. Where did I talk about this? Well, you can see the discussion maybe at Fourier discrete. Okay, let's see. In the Fourier discrete, let me find, where did I talk about it? Let me pause first. Now, you realize that the pole and zeros are this diagram. And remember that you can actually draw a 3D diagram of this pole and zero. And as you're traveling along the unit circle along this line, you are also traveling along this horizontal line here. Okay? And what does that mean? That means that values of Hz along this unit circle is exactly the H, E, J, omega. All right. So we are going to plot H, E, J, omega. By plotting the H, E, J, omega, we'll understand what type of filter it is. What type of filter? What type? How many types of filters are there? There are 4 different types of filters typically. A filter that only does this from 0 to, let's say, pi over 2 minus pi over 2. Here is omega. This is a gain 1 low pass filter. The reason why it's called low pass filter is because the low frequency has gain 1 and the high frequency has gain 0. So only low frequency is passed. What about the other one? 0 WC. WC stands for cut off frequency. And then we are only interested in up to pi over 2. Again, this is a high pass filter. A high pass filter means that at high frequency, the signal is passed through. And then there are 2 others. One is called the band stop, means at pi over 2. From here to here, the frequency are attenuated dramatically. And here to here, the frequency is only passed through, but here is attenuated. So this is a band pass. This is a band stop. So the question is, only by inspecting this figure, can we determine what type of filter it is? Now, you have to study the math, but the interpretation is actually very clear. Wait, let me find as we are moving along, uh, okay, I'm going to use my arrow. You can see my arrow? As we are moving along this position, the word moving along means as we are evaluating Hz at this frequency, you realize that we are very near a pole. The nearer we are to the pole, the larger the output value is. So as we nearest to the pole at this point, the output will be very big. And then the further we go from the pole, it becomes smaller and smaller and smaller. And in fact, when we touch a zero, the output is zero. So what is the answer? So I'm going to use MATLAB to solve the problem. But of course, if you, in the exams you don't have MATLAB, you are guessing. And later on, you realize that, in fact, I'm going to ask you to evaluate as well. Okay, so let's try. Okay. All right, so we have FV2. Now, I'm going to punch in a sequence of numbers. So what is a sequence of numbers I'll punch in? It is exactly these numbers. So the number is 1, 1, 0 for the top, and the bottom is 1 minus 1.6 plus 0.89. What does this number represent? In fact, you see, it represents the coefficients of the Z transform. So let's try 1, 1, 0, 1 minus 1.6, 0.89. And for sanity check, we'll see whether we get our, what do you call this, pole and zero correct first. So you see 1, 0 here was like what we have said. Let me show you the figure I've drawn. 1, 0, 1, 0. What about this guy? 1, 0, 1, 0. What about the pole? 0 0.8, 0 0.5, 0 0.8 minus j 0.5. So we got it correct. So we know that it is correct. So as we are moving from 0 to pi over 2 to pi, we are going to plot h of z magnitude. So remember what I said? As we are traveling along omega from 0 to pi, as we are nearing the pole, it peaks and then it comes down again. So some of you all may say that this is a band pass filter, passing from this band to this band. Or some of you all will say it's a low pass filter because at a low frequency and then high frequency is attenuated. Both are somewhat right because this actually it looks more like a band pass filter. But even if you say it is a low pass filter, we'll give you some marks because actually you see, actually is at a low frequency is poor response. At a certain frequency, wow, is huge. And then after that is attenuated again. So this is like actually more like this figure, the band pass filter. Okay, now I pause here for a little while. I'll take questions now. Okay, so I'm going to show you my working now. So from this question, I've gone into the evaluation of HEJ omega at different frequencies. First, I try the frequency at 0. and then I get this answer. I plot this value, and then for different values of frequency omega, I can evaluate and I can get different value. So this is the trick how to find what type of filter it is. Basically, it is a brute force approach to evaluate HEJ omega at different frequencies. Finally, in the last example, I asked you what is HEJ omega at omega equals to pi. Now, first is EJ omega at omega equals to pi, basically means substituting pi into omega, and you know EJ omega is minus 1 plus J0. When we substitute into HEJ omega, the first term is minus 1 square, second term is minus 1, third term is 0. Therefore, the numerator becomes 0, and therefore the whole expression becomes 0. Okay. Is there a way to use the equation to get the magnitude? Yes, there is. Guess,
Yeah.
Sebastian. Guess. Now you know how to calculate HEJ omega. So tell me, what value would make this HEJ omega the biggest? This is not a trick question. Sebastian, come. Using the pole information. Yes, correct. Or, 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 or making this guy smallest. When he is the smallest, typically, therefore, the whole system would be the biggest, right? So when is he the smallest? When omega is nearest to the pole. Okay, so once you understand that, that is why we can interpret from the pole zero diagram what's happening. Hong Viet, did I also answer the same question to you?
Yes, Prof.
Is it clear now? I hope it's
Yes.
clearer.
But it's the part C that has the most issue because I think it was a Fourier question, so it's
Mm,
a bit.
okay.
At that time when I was attempting a question, I didn't know that it was actually a Fourier series and not a time series.
Mm, okay.
So a bit issue over there.
Okay, can. So I explain what Hong Viet is asking for. So let's go to the exam question again. And so this is the exam question. And then, so we have done 1A and 1B. All right, 1C. Okay, let's do 1C now. Can? Now, the question is like this. First, the filter has been described to us, LTI system. And now XN is given to us. And then now we're asked, what is YN? In fact, this is exactly the same question as the lab, right? Almost. Almost. Okay, let's try. First, you draw the system. And this is H of N. And this is X of N. And then X of N is equals to 1 plus 1 EJ pi over 2N plus 1 EJ pi N. So what is Y of N? And then you will think that it is X of N convolved with H of N. And then you realize that you can't do this approach. The reason being that although technically this is correct, but H of N is what? Guys, what's H of N? Finite or infinite impulse response? Somebody tell me, please. Somebody. Oh, am I recording again? Okay, I'm recording again. Somebody, can you help me? Hong Yet. I only remember your name. Infinite. Yes, Wilbert. Good. Infinite. The reason why it's infinite is that once there's a pole, then not typically we get infinite. Of course, for sanity check, then I always pull out MATLAB, and then now we have this guy, and I fire this button, and then what do? I go pump. Tok, 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 tok. Oh, okay. So you think it goes to zero? No, it is some very small value, but it will never go to zero. Okay, so this is infinite impulse response. So there is no chance in hell, right? I can do this guy properly. Okay, so instead, let's do it in the frequency domain. Or let's do it in the h of z first. If I have the h of z, I have y of z, I have x of z. So this is one way you can do it. But actually, maybe we are not interested in this. We'll do Fourier transform. H of z become h of ej omega. And then this is y ej omega. And then this guy is x of ej omega. What is x ej omega? It is the discrete time Fourier transform of x of n. Why discrete time Fourier transform? Because this guy is periodic or aperiodic, guys? Actually, it's periodic. Huh? See, one is just one line, right? And then this guy is periodic, right? He's repeating after every, how many samples? 4 or 8? Yeah, 4 samples. This guy is repeating after every 2 samples. So the whole thing is repeating after every 4 samples. So, right. Now, the interesting thing is that in the frequency domain, what does Hej omega reveal? Hej reveals how Xej omega will change at each frequency. What does that mean? You realize that X of n, it composes of only three signals. 1 Ej pi over 2n plus 1 Ej pi over n. There are 3 frequencies. In fact, the first one is a trick. Yeah, can you see now? Oh, the first frequency is actually 0. The second frequency is pi over 2. The third frequency is pi. I am sending a signal that has 3 frequencies. One is at 0 radian per sample, one is pi over 2 radian per sample, the last one is pi radian per sample. So what do I need to do? So I can, y of n can simply be 1 ej0n, which is the input signal, multiplied by h of ej omega equals to 0. This will reveal the signal, how this signal is being changed by the filter with this characteristic. The second guy times h ej omega equals to pi over 2. And the last guy and then that's the answer. Then of course you say, what are these value? Then did I not calculate it for you here? Okay, but I only calculate the magnitude. So you also need to calculate the phase as well. So Hong Viet, did I answer your question now? Hong Viet. Hello? Did I lose your? Are we still online? Yes. Okay, good. Sebastian, do you figure out how to do question 1C already? Yes. Okay. So maybe I'll tell you the answer and then you guys go back and check. Okay. So I'm going to tell you the answer and then you guys can check. The answer is, let me pull it here and then we can all go home. So yn is equals to, the first one is 1 ej0n multiplied by 6.896 ej0. Okay, plus 1 ej pi over 2n, and this guy is 0.8818 ej minus 2.28. Okay, and the last one plus 1 ej pi n times 0. Okay, now if you guys is confused with this guy, 0.8818 and minus 2.28, let's go to pi over 2n using MATLAB. Okay, let's go to the magnitude and let's go to pi over 2, which is 0.5 pi, and the gain is should be 0.88. Correct. Now let's go exactly to the correct place. So that 0.8. Wow, come on. Yeah, you guys see the picture, right? It's about 0.87, 0.88. So my calculation is not so off. What about minus 2.28? Where is it? Go to the face. So this second, you guys are watching my screen, right? Okay, the face. And I'm going to go to here and see, minus 2.28. Okay, the phase is here. Sometimes you will click this third button, which shows you the magnitude and the phase together. So I'm interested in 0.5 radian. And then, oh, come on. Okay, so 0.87. Yeah, I mean, I don't know. 0.87, 0.88 something. Okay, 0.88 minus 2.28. Okay, so we get the magnitude and the phase. Okay, so with that, I've answered one ABC in about 40 minutes. So this is way too long, okay? You don't have this amount of time to do this question. It should be done very, very fast. 1D, 1D is, 1D, let me see 1D. Where is the question 1D? HN is, how to do HN? This is by brute force, okay? So by brute force means that you plug in, what the easiest would be this example. In the tutorial, I've already shown you the easiest way is you draw the figure of the system and you plug in xn as an impulse and you start to evaluate, assuming that the system is relaxed for all values first. And then you'll get h of n. Then for sanity check, go to MATLAB and type this button and then you'll plot. And here I'm asking you to do only like, how many numbers? Maybe 0 to 3. So you only need 0, 1, 2, 3 numbers. What about the rest? Actually, there's a closed form solution, but it's not so easy. In fact, it's very hard to find a closed form solution. Not easy at all, okay? So that's why if you get this part right, you get at least 3-4 marks. And we only ask you to discuss how to find the closed form solution. We didn't even ask you to find the closed form solution, okay? The discussion of how to do is actually here, exactly here. You see, we will ask you to break the whole system into these roots of the polynomial, and then we ask you to find the inverse Z transform to get h of n. Okay. Did I answer you, Hong Viet? Okay, with that, let me now pause